It always fascinates me how something like control systems, which sounds, well, kind of technical, is really all about this very human desire to make things easier for ourselves.
It's true. I mean, we've been kind of dreaming about self-operating gadgets since like Aristotle, right?
Right.
But it's more than just convenience. Control systems are about achieving this level of precision and reliability that we just can't get manually. Um, think about like those incredible straight lines in Egyptian architecture.
Oh, yeah.
That's thanks to early control systems.
Right. Even those ancient water clocks Vitruvius described, they weren't just telling time, right?
Right.
They were using feedback to like regulate the water flow and stay accurate. I mean, that blows my mind. It's like a 2,000-year-old ancestor to like the systems that we rely on every single day.
Exactly. And that feedback loop, that's really the key, right? You've got a
Mhm.
sensor, it's checking the output, it's comparing it to what you actually want, and then it's adjusting things to stay on track. It's this really elegant principle that makes everything from like a simple thermostat to a self-driving car, it makes it all possible.
Speaking of which, I mean, it's so fascinating to kind of trace how these systems have evolved over time, right? We go from like Cornelis Drebbel back in the 17th century, right?
Mhm.
Tinkering with like temperature control.
Mm.
And then boom, James Watt comes along with his game-changing centrifugal governor for steam engines.
Yeah.
Talk about a pivotal moment in history, right?
Well, absolutely. Watt's governor, it was a total breakthrough, right? Because it could automatically regulate the speed of a steam engine,
Yeah.
even with these changes in load, right?
Mhm.
Before that, it was all manual adjustments, which, as you can imagine, it wasn't very efficient or reliable.
No, not at all. And even then, right? I was reading the Watt's governor. It had a quote moderate operating condition and a small operating range.
Yeah.
Can you imagine, like engineers today, getting away with that kind of description?
No
It
way.
makes you really appreciate how much effort, how much like trial and error went into refining those early designs.
Totally.
What were some of the biggest hurdles that those early engineers, what were they up against? What did they have to overcome?
Well, for one thing, those early control systems, they were very, very specific to whatever they were like designed to do. You know what I mean? There
Yeah.
wasn't a standardized way to like design or analyze them. It was a lot of trial and error, honestly. Each engineer, it was like they were starting from scratch almost.
So so by the time like the 20th century rolls around and you've got control systems popping up everywhere, you've got them in factories, you've got them on ships, you've even got them in early telephones. There must have been a real need for some kind of, I don't know, like a common language
Yeah.
to talk about these things, right? Like,
Yeah.
how do you even begin to discuss these things in a consistent way?
Exactly. And that lack of like a unified theory, it was becoming a major bottleneck.
Yeah, I could see that.
You had this explosion of practical applications, but there was no like shared vocabulary. There was no real mathematical framework to even guide their development.
So what changed? How did we go from this wild west of control systems to the more structured field that we know today?
Well, that's where what we call the classical period comes in, roughly from the mid 1930s to the 1950s.
Hello?
This is when those real pioneers, people like Harold Stephen Black and Harry Nyquist, they really laid down like the foundation for modern control theory.
Ah, Black. He's the one behind the negative feedback amplifier, right?
That's the one.
Which on the surface sounds kind of technical,
Yeah.
but when you really think about it, that's the thing that revolutionized long distance phone calls.
Exactly. And it just highlights how much of an impact control systems have had. Like before negative feedback, long distance calls, they were just plagued by signal distortion and noise.
Awful.
Black's work, it allowed for the amplification of signals without all that unwanted noise. And that's how we got those clear, stable phone calls that we totally take for granted today. Was a game changer. And it all stemmed from understanding how to use feedback effectively.
So Black tackled the clarity problem,
Architecture.
right? What about Nyquist? What
Yeah.
was his big contribution?
Nyquist, he cracked the code on stability. You see, feedback systems, they can be a little tricky because sometimes instead of smoothly correcting things, they overcompensate and they start oscillating out of control.
Oh no.
Right. So Nyquist, he developed a way to analyze a system and determine whether it would be stable, well behaved, or if it would be prone to those crazy oscillations.
So it's like before Nyquist, you build a system, you turn it on, and you just kind of cross your fingers and hope for the best.
Pretty much.
And then Nyquist comes along, and he's like, hold on, I can actually tell you beforehand.
Yeah.
This thing's going to work the way it's supposed to work.
Precisely. His, what we call the Nyquist stability criterion, it gave engineers this powerful tool to design systems that behaved predictably. It was a huge step towards making control systems more reliable and frankly less prone to, exploding.
That's always a plus.
Right.
Okay, so the classical period, it brings like some much needed order to the chaos.
It does.
But I'm guessing the story doesn't like end there, does it?
Yeah, you're right. Things were really just getting started. After the war, you had this surge in complex systems. We're talking things like jet aircraft, industrial processes that were way more intricate than anything that came before. This is where we enter the era of what we call modern control, which really grapples with things like non-linearity, which is where a system's behavior changes in unpredictable ways.
Oh, yeah.
And the ever-present noise of real-world conditions.
Right, because a simple feedback loop, it's probably not going to cut it when you've got like dozens of variables all interacting with each other in these crazy complex ways.
Exactly. We needed more sophisticated mathematical tools. We needed computational approaches, and that's where those giants, people like Richard Bellman, Rudolf Kalman, and Lev Pontryagin, they come in. They brought tools like dynamic programming, filtering techniques, things like the maximum principle to bear on these increasingly complex problems.
So these advancements, they weren't like just theoretical, right? These guys, they were tackling real world problems with this stuff.
Oh, absolutely. Like take Kalman, for example.
Okay.
His work, it led to what we call the Kalman filter, right?
Mm-hmm.
It's this incredibly powerful tool for estimating the state of a system, even when you've got like noise,
Yeah.
uncertainty, all that stuff messing with your measurements.
So it's kind of like trying to track a moving target, but you're in a blizzard or something.
Yeah.
You're not getting like perfect information, but the Kalman filter helps you kind of make sense of what you are getting.
Exactly. It's used in everything. I mean, everything from like navigation systems to like financial modeling.
Right.
It's a perfect example of how, these theoretical advancements in control theory, they've translated into these practical tools that we rely on, I mean, every single day, really.
It's amazing how much of that stuff kind of goes on behind the scenes, like we never even think about it. Okay, so we've got like a good handle on the historical evolution of control systems now, right? But
Yeah.
But I'm curious for someone like me who's trying to like wrap my head around the whole field,
Yeah.
What are the main categories? What are the buckets that we should be thinking about?
Well, one really fundamental distinction is between what we call controllability and what we call optimization.
Okay.
Controllability, that's all about like whether or not you can even steer a system to a desired state. Like can you get it to do what you want it to do? At least in principle, right?
So like with my old car, right? Like can I even get it up to highway speed?
Exactly.
Let alone like worry about if that's the most fuel efficient way to drive, right?
Perfect analogy. So once you know a system, it's controllable, right? That's when optimization comes in.
Right.
How do you achieve those goals, but in the most efficient way possible, the fastest, the least expensive, you know?
So in the case of my car, optimization would be like figuring out the best route to take, the best speed to drive at, the best driving style, all that stuff to maximize my fuel efficiency.
Well, exactly.
It's about finding the smartest way to reach your goal.
Precisely. And these concepts, they apply whether you're talking about like, a simple water tank maintaining a specific level or like a complex robot navigating, a crowded environment, whatever it is.
Speaking of applications, it seems like control systems are like everywhere these days. I mean, you can't swing a cat without hitting something that's got like a control system in it. So give us a tour of the landscape, right? Where are these systems having like the biggest impact?
Well, you're right. They are everywhere. Like robotics is a huge area, obviously. I mean, you've got everything from like, industrial robots working in factories to like those robot vacuums that are, roaming around people's homes. They all rely on sophisticated control systems, right? To move precisely, to interact with their environment, to achieve these complex tasks.
And it's not just about like the robots themselves, right? Even something like a self-driving car
Yeah.
that relies heavily on control systems as well.
Absolutely. A self-driving car, it's basically a robot on wheels, right?
Right.
It needs those control systems to process data from sensors, to make decisions about steering and speed, and to navigate these complex environments. It's a prime example of how control systems are really like pushing the boundaries of what's possible.
Right. It's taking those principles that we talked about before, right? The feedback loops, the stability analysis, the optimization, all that stuff. And it's applying it to this incredibly complex, like real world problem.
Yeah.
Which is really cool to see. What other fields really benefit from this technology?
Well, space exploration is another great example. Think about the precision that's required to control a spacecraft in orbit,
Oh yeah.
or to like deploy a satellite, or to land a rover on Mars, for example. I mean, those are incredibly challenging control problems. They push the limits of our understanding.
It's funny because we often like take those achievements for granted now,
Yeah.
Like, oh, another rover on Mars, big deal.
Yeah.
But when you really think about the complexity of controlling something that's millions of miles away,
Yeah.
it's kind of mind-boggling, right?
It really is. And those advances in space exploration, they often trickle down to more, I guess you could say, everyday technologies, right? I mean, think about something like a CD player.
Oh yeah.
It uses control systems to keep the disc spinning at a constant speed, so you get that accurate data reading. Or laser surgery,
Yeah.
where control systems guide lasers with just incredible precision. The applications are truly vast. I mean, it's hard to think of an area of technology that doesn't benefit from control systems in some way.
It's really a testament to how versatile these systems are,
Yeah.
But with all this complexity, I mean, are there limitations? What are some of the major challenges that control system engineers that they're facing today?
Well, one of the biggest ones is definitely dealing with nonlinearity.
Yeah.
Real world systems, they're rarely as simple and predictable as the models that we use to design them. Their behavior can change, I mean, dramatically, depending on operating conditions and all sorts of other factors.
So it's like your control system is like working great in the lab, right?
Right.
Everything's nice and controlled.
Yeah.
And then you take it out into the messy, unpredictable real world, and suddenly it's a whole different ball game.
Exactly. And another major challenge is dealing with noise, which is just like the uncertainties and disturbances that are just, they're always present in real world measurements.
Right.
Our sensors, that they're never perfect, and unforeseen events, they can always throw a wrench in the works.
So it's not just about designing a system that works, in theory. It
Yeah.
has to be a system that can handle the unexpected and still achieve its goals.
Right. Exactly. And this is especially challenging as we move towards more interconnected systems. You know what I mean?
Mm.
Think about things like smart grids, traffic management systems, even financial markets.
Yeah.
These are all like networks of control systems that need to work together, and they need to work together seamlessly and reliably.
And that interconnectedness just it amplifies the complexity, right? Like a small hiccup in one part of the system
Yeah.
can just cascade and cause all sorts of problems elsewhere. It's like this delicate balancing act, but on a massive scale.
Precisely. So we're not just talking about, individual control loops anymore. We're talking about designing systems that can adapt, that can learn, that can cooperate within these massive networks. It's a fascinating field, and it's evolving incredibly rapidly.
Now, we've talked a lot about these complex digital systems, right? But what about like the older analog control systems? Are those still relevant in this age of like microprocessors and sophisticated algorithms and all that?
That's a great question. Analog control systems, they rely on like these continuous signals and analog circuits. They were really the workhorses of the past. I mean, think of like those old thermostats with the mercury switches.
Oh, wow.
Those are examples of analog control.
So it's like the difference between like a vinyl record and a digital music file.
Yeah.
Right. Like both of them can play music, but they use fundamentally different technologies to do it.
You got it. And modern control systems, they're primarily digital. They leverage the power of microprocessors, digital sensors, and sophisticated algorithms to achieve greater precision, more flexibility, and the ability to handle those complex nonlinear systems that we were talking about. So while analog systems, they still have their place in certain niche applications, I think it's safe to say that the future of control systems, it's definitely digital.
It strikes me that all this talk about digital versus analog, it really kind of boils down to how we translate our knowledge into action.
That's a great way to put it. I mean, control systems, they're really at their core about capturing our understanding of a system, right? It's physics, its limitations, its goals, and then encoding all that knowledge into a form that can actually like make decisions, take action in the real world.
And as our knowledge grows and as our computational tools become more powerful, the things that we can control, they become increasingly complex, don't they?
Exactly. Every new breakthrough in control theory, every new algorithm, every jump in processing power, it just opens up all these new possibilities. And we're not just controlling like individual machines anymore, right? We're talking about entire systems, optimizing them in ways that would have been, I mean, unimaginable just a few decades ago.
It makes you wonder where this is all heading.
Yeah.
What are some of the grand challenges, the really big dreams that control systems might tackle in the future?
Well, one area where control systems have just huge potential is in addressing like these global challenges that we're facing, right?
Okay.
I mean, imagine systems that could help us like manage climate change, for example,
Oh, wow.
or optimize like resource allocation, or even coordinate global economic activity to make it more sustainable, more resilient.
It's a future with like incredibly high stakes, right? I mean, the power to control systems that complex, it could lead to some amazing advancements.
Yeah.
But it also comes with a huge amount of responsibility, doesn't it?
Absolutely. As we push the boundaries of what we can control, we need to be incredibly thoughtful about the ethical implications, right? It's not just about like making systems efficient. It's about making sure that they align with our values and that they contribute to a better future for everyone, really. And that requires a deep understanding, not just of the technology itself, but also of its potential social and environmental impact.
It's a powerful reminder that control systems, for all their technical sophistication, they're ultimately just tools, right?
Right.
And like any tool, I mean, they can be used for good or for ill. It's up to us. It's up to us as a society to kind of guide their development and to make sure that they're used responsibly.
I couldn't agree more. The future of control systems, it's not just about like writing more elegant algorithms or building faster processors, right? It's about having a vision for how we want to use this incredibly powerful technology to shape a better world.
Well said. It's been really fascinating to explore this field with you, from those ancient water clocks that we were talking about earlier to like the mind-boggling potential of controlling systems on a global scale. It's really been quite a journey.
The pleasure was all mine.
Yeah.
It's a field that's constantly evolving. It's full of surprises. It's full of challenges, but ultimately it's a testament to human ingenuity. It's a testament to our drive to understand and to shape the world around us.
Yeah.
I couldn't agree more. And on that note, we're going to wrap up this deep dive into the world of control systems. We hope you found it insightful. And who knows, maybe it's even sparked some ideas for how you might use this incredibly powerful technology to make your own mark on the world.